Engineering materials get 2 to 3 marks every year. Crystal structures, material properties and testing, phase diagrams, heat treatment, powder metallurgy only for gate. IES, these all topics are there. Plus nanomaterials, preventive methods of corrosion is there. Paper 1 14 questions, 28 marks. Paper 2 8 questions, 16 marks. These are for IES prelims. Mains 60 to 70 marks. GSCA paper 1, GS General Science, Basics of Material Science and Engineering, Conducting Materials, Conductors, Superconductors, Semiconductors, Dielectric Materials, Magnetic Materials, Polymers, Ceramics, Composites. First, let's see syllabus, complete syllabus of GATE, which is common for IES also. Materials. Based on arrangement of atoms, the solid materials are two types: crystalline material, non-crystalline material, or amorphous material. In crystalline material, atoms are arranged in regular periodic manner. In non-crystalline material, atoms are arranged in irregular manner with more void space. The crystalline material have high strength because of more number of bonds per unit area. The non-crystalline material have low strength because of less number of bonds per unit area. The crystalline material are anisotropic in nature, that is, material property are different in different direction. The non-crystalline material are isotropic in nature. The crystalline materials have sharp and high melting point temperature. The non-crystalline materials have low and range of melting point temperature. Crystalline example: all metals, quartz, some of ceramics, none of polymers. Non-crystalline material example: plastic, rubber, glass. Unit cell. Smallest number of atoms are arranged in repeating manner. Shape parallelopoid. And the parallelopoid means this: ABC lattice parameters alpha, beta, gamma, interfacial angles n is equal to 6, which is maximum number of parameters required to describe a unit cell. Bravis lattice systems type of unit cells. Total number of lattice systems 14. Basic or primary lattice systems 7. First cubic system: A is equal to B is equal to C, alpha is equal to beta is equal to gamma is equal to 90 degrees, n is equal to 1. Only the if we know A, we can describe the system. Triclinic: A not equal to B not equal to C, and alpha not equal to beta not equal to gamma not equal to 90 degrees, n is equal to 6. The triclinic system is most complex type of lattice system because they require all 6 lattice parameters to define it. Tetragonal system, it is similar to RTC bus: square then a rectangle. Here A equal to B not equal to C, but alpha equal to beta is equal to gamma is equal to 90 degrees. Here n is equal to 2. Orthorhombic system, matchbox. It is similar to matchbox: A not equal to B not equal to C, alpha equal to beta equal to gamma is equal to 90 degrees, n is equal to 3. A, B, C we should know. Hexagonal system: A equal to B not equal to C, alpha equal to 120 degrees, beta is equal to gamma is equal to 90 degrees, 2, n is equal to 2. We should know A comma C. Rhombohedral system: A equal to B equal to C, alpha equal to beta equal to gamma not equal to 90 degrees, n is equal to 2. We should know A and alpha. The rhombohedral system. Monoclinic system: A not equal to B not equal to C, alpha equal to beta equal to 90 degrees not equal to gamma, n is equal to 4. A comma B comma C comma gamma. Type of crystal structures. Simple cubic structure. SC, in a simple cubic structure, 8 atoms are arranged at 8 corners of unit cell. Every corner atom touches with other 3 nearest corner atoms with the unit cell. with the unit cell. The number of atoms or lattice points required to form a simple cubic structure is n is equal to 8 atoms. Here 8 atoms required, top 4, bottom 4. The effective number of atoms present inside the unit cell n is equal to 1 by 8 into 8 is equal to 1 atom. The relationship between lattice parameter A and atomic radius r is A is equal to 2r. Yes, this is A and 2A is equal to 2R. Bond length, it is shortest distance between two atoms in a material. The bond length of simple cubic structure is 2R or A. Atomic packing factor or packing density, it is fractional volume of unit cell occupied by atoms. APF is equal to total volume of atoms inside unit cell by volume of unit cell. N into 4 by 3 pi r cube by a cube. Here n is 1, effective number of atom 1 into 4 by 3 pi r cube, as they are spheres, by A is 2r, so 2r whole cube. APF is equal to 0.52. Percentage empty space is equal to 1 minus APF into 100 is equal to 48%. Coordination number, it is the number of nearest neighboring or touching atom to a specified atom of a material. The coordination number of simple cubic structure is 6. Note the coordination number is constant for material except surface atoms. Example polonium. Example of simple cubic is only once polonium. Coordination number means we can assume a corner atom in your room. It will be connected to six atoms like bottom, top, this side, and that side. Like you have to assume cubes keep on repeating, and if you assume one corner atom, we can get coordination number 6. Example, we have only one polonium. Body centered cubic structure. In body centered cubic structure, 8 atoms are arranged at 8 corners of unit cell, and one atom is arranged at body center of unit cell. In BCC structure, all 8 corner atoms touch with the body center atom, but no two corner atoms are touching with each other. No two corner atoms are touching with each other, but the center atom will touch with all these 8. N capital N is equal to 9 atoms, as there are 9 atoms in this. Effective N is equal to 1 by 8 into 8 plus 1 into 1 is equal to 2 atoms. As middle one is completely inside it, everyone will have 1 by 8 of contribution. Relation between A and R. df square is equal to df square is equal to a square plus a square, but here db, body diagonal, db square is equal to a square plus a square plus a square. 4r whole square is equal to root 3a square, as 2r r. 4r is equal to root 3a. Bond length is equal to 2r from here to here. 2r is equal to root 3a by 2. APF is equal to n into 4 by 3 pi r cube by a cube is equal to 2 into 4 by 3 pi r cube by a cube is equal to 0.68. Percentage empty space is equal to 32%. Coordination number is equal to 8. Examples you can remember by TISC: tungsten, iron, sodium, chromium. Tungsten W, iron Fe, sodium Na, chromium Cr. Question: determine free space present in a unit cell of tungsten material with an atomic radius of 0.14 nanometer. First we have to identify that tungsten is in BCC structure. So 4r is equal to root 3a. A is equal to 4r by root 3. We will get a 0.3233 nanometer. Empty space is equal to 0.32 a cube, as 68% is APF and 32% is percentage of empty space. 0.32 a cube is equal to 0.0108 and nanometer cube. Volume of unit cell occupied by atoms is equal to n into 4 by 3 pi r cube is equal to a cube into 0.68. Face-centered cubic structure. In face-centered cubic structure, 8 atoms are arranged at 8 corners of unit cell, and 6 atoms are arranged at centers of six faces. At centers of six faces in FCC, every face-center atom with four face corner atoms and four other nearest center atoms within the unit cell. Within the unit cell, n is equal to 8 plus 6, 8 corner and 6 face centers. 8 plus 6 is equal to 14. Small n is equal to 8 into 1 by 8 plus 6 into half, as it is contributed to half. 3 plus 1 is equal to 4 atoms. Relation between a and r, df square is equal to a square plus a square. 4r whole square is equal to 2a square. 4r is equal to root 2a. Bond length is equal to 2r, or root 2a by 2 is equal to a by root 2. Atomic packing factor is equal to n into 4 by 3 pi r cube by a cube is equal to 0.74. Percentage empty space is equal to 26%. Coordination number is equal to 12. Example, NALCO, nickel, aluminum, copper plus face. So gold, you remember by face beauty, gold, silver, platinum, noble metals. Nickel, aluminum, copper. Diamond cubic structure, DC structure, is also known as face-centered tetrahedral structure. In diamond cubic structure, 8 atoms are arranged at 8 corners of unit cell. 6 atoms are arranged at centers of 6 faces. 4 atoms are arranged inside unit cell on body diagonal. Each body diagonal atom touches one corner atom and three nearest face center atoms within the unit cell. Each tetrahedral atom is located on a body diagonal with a coordinate of a by 4, a by 4, a by 4 from corner. N is equal to 8 plus 6 plus 4. 8 corners, 6 face centers, then 4 inside is equal to 18 atoms. Small n is equal to 1 by 8 into 8 plus 6 into half plus 4 is equal to 8 atoms. Relation between a and r, 2r is equal to root of a by 4 minus 0 whole square plus a by 4 minus 0 whole square plus a by 4 minus 0 whole square. 2r is equal to root 3a. 8r is equal to root 3a. Only this is important. 8r is equal to root 3a. Bond length is equal to 2r or root 3a by 4. Atomic packing factor is equal to 8 into 4 by 3 pi r cube by a cube is equal to 0.34. Percentage empty space is equal to 0.66 into 100 is equal to 66%. Coordination number is equal to 4. Example, diamond, silicon, germanium. Note, zinc blend structure. In zinc blend structure, 8 zinc atoms arranged at 8 corners of unit cell and 6 zinc atoms are arranged at centers of 6 faces. 4 sulfur atoms are arranged inside unit cell on 4 body diagonals. Each sulfur atom is located at a coordinate of a by 4, a by 4, a by 4 from corner. The arrangement of atoms in ZNS structure is similar to diamond cubic structure. Example, compounds of third and fifth group elements, gallium arsenic. The strength of material is independent of atomic packing factor. The atomic packing factor gives information about arrangement of atoms in a unit cell. The vector between shortest distance atoms in a face-centered cubic system is face-centered cubic system is along diagonal, along any one diagonal. So IA by 2 plus KA by 2, this is for FCC. We can also find this is for diamond cubic structure, this is for simple cubic joining two atoms, this is for along body diagonal, so BC, this is for BCC. Hexagonal close packed structure, A equal to B and not equal to C. A, B, C, or A, B are equals, this is C. top six atoms, and in the center one, and there will be three atoms in the middle. A by 2, A by 2. In a hexagonal close packed structure, 12 atoms are arranged at 12 corners of unit cell. Two atoms are arranged at centers of two base planes, and three more atoms are arranged inside unit cell in a triangular form at a distance of c by 2 from base plane middle from base plane. In a hexagonal close packed structure, every base center atom will touch with six corner atoms and three middle atoms within the unit cell. N is equal to 12 plus 2 plus 3 is equal to 17 atoms. Small n is equal to 1 by 6 into 12 plus half into 2 plus 3 is equal to 6 atoms. Relation between AC and R. A is equal to 2R. C by A is equal to root of 8 by 3 is equal to 1.634. We can find by this is A is equal to 2R. This is A is equal to 2R. C by 2 X. Top this X. A square is equal to C by 2 whole square plus X square. This is 30 degrees, this is 60 degrees. Cos 30 is equal to A by 2 by X is equal to root 3 by 2. X is equal to A by root 3. A square is equal to C by 2 whole square plus A by root 3 whole square. C square by A square is equal to 8 by 3. C by A is equal to root 8 by 3 is equal to 1.634. Volume of HCP is equal to 6 into root 3 by 4 A square into C. 6 into root 3 by 4 A square into C. Root 3 by 4 A square. That is by these equilateral triangles, 6 equilateral triangles of A. So root 3 by 4 is 6 into root 3 by 4 A square into C. Bond length is equal to 2R or A is or C by 1.634. Atomic packing factor is equal to 6 into 4 by 3 pi r cube by 6 into root 3 by 4 A square into C is equal to 0.74. Percentage empty space is equal to 26%. Coordination number is equal to 12. Example CO, zinc, cadmium, beryllium, zirconium, magnesium, titanium. Determine volume of unit cell in a zinc material with an atomic radius of 0.135 nanometer. The zinc is HCP structure with C by A of 1.634. C comma A are lattice parameters. VHCP is equal to 6 into root 3 by 4 A square into C. A is equal to 2R is equal to 2 into 0.135 is equal to 0.27 is equal to 0.08356 nanometer cube. Structure of graphite. In graphite, every carbon atom is covalently bonded with three other carbon atoms by sharing three valency electrons from each carbon and forms simple hexagonal layer. These layers are bonded with weak van der Waals forces. Graphite is used as solid lubricant because to break van der Waals bonds between hexagonal layers requires low energy. Graphite is a good electrical and thermal conductor because of free valency electrons. Free single covalent bonds plus van der Waals bond. These van der Waals bonds hexagonal. In diamond, every carbon atom is covalently bonded with four other carbon atoms by sharing four valency electrons and forms tetrahedral structure or diamond cubic structure. The diamond is hardest and strongest bulk material because in diamond bonds are arranged in well structured manner. The diamond is an electrical insulator because no free valency electrons in it, but it is highest thermal conductor because of presence of lattice vibrations or phonons. n is equal to 8, j is equal to 11, degree of freedom is equal to 3 into 8 minus 1 minus 2 into 11 is equal to minus 1. Okay, let's see all structures combined in a table. Simple cubic, capital N is equal to 8, effective number of atoms 1, A is equal to 2R, bond length 2R or atomic packing factor 0.52, percentage empty space 48%, coordination number 6, example only polonium. BCC n is equal to 9, effective number of atoms 2, relation between A and R, root 3A is equal to 4R, 2R or bond length 2R or root 3A by 2, APF 0.68, percentage empty space 32%, coordination number 8, examples disc, tungsten, iron, sodium, chromium. FCC n is equal to 14. Effective number of atoms 4. Root 2a is equal to 4r. Bond length 2r or a by root 2. Atomic packing factor 0.74. In percentage empty space 26%. Coordination number 12. Coordination number 12 because each face center atom will be in contact with 4 atoms. Each face center atom will be in contact with 12 atoms. Nalco, nickel, aluminium, copper, gold, silver, platinum phase. HCP n is equal to 14. Effective number of atoms 6. A is equal to 2R. C by A is equal to 1.634. 2R or A or C by 1.634. Atomic packing factor 0.74. Percentage empty space 26%. Coordination number 12. Cobalt, zinc, cadmium, beryllium, zirconium, magnesium, titanium. Diamond cubic structure n is equal to 18. Effective number of atoms 8. 8R is equal to root 3A. 2R bond length 2R or root 3A by 4. Atomic packing factor 0.34. Percentage empty space 66%. Coordination number 4. Diamond, silicon, germanium, zinc blend ZNS. Holographic direction. It is line or vector drawn from origin to endpoint within a unit cell. Representation of single direction square bracket x y z, representation of family of direction this bracket x y z, this bracket. Here it is line, so these are lines only, these two are lines only. And for example, if 120 has to be represented, then it should be represented by 1 by 2, 2 by 2, 0 by 2. Zero, if one it is represented like 120, then 0 on z axis, x axis half, y axis 1. Draw a line. If this line has to be represented, then 0 1 3 by 4, which is equivalent to 0 4 3 multiply with 4, and this is to be represented x, x is a by half, y is y is 1, y is 1, z 0, so 120 represented by 120. Let's go for reverse. If 4 to 1 is given, then divide by 4, 1 half 1 by 4, so x 1 here z half here, then y 1 by 4. Draw that line, imagine like in 3D. 1 bar 0 1 bar, that means bar means negative. From origin go in opposite direction, x is equal to -1, z is equal to -1. If this is to be represented, minus a by 3 comma 0 comma minus a, 1 bar comma 0 comma 3 bar, x is equal to minus a by 3, z is equal to minus a. Linear density is equal to number of atoms in direction by length of direction. If it crosses like this, then half. If it crosses fully, then 1. If it doesn't pass through center, then 0. Determine linear density of simple cubic structure within with an atomic radius r for given below crystallographic directions. 1 0 0 a is equal to 2r, 1 0 0 is this. So length, so linear density number of atoms in direction by length of direction. This is half half. So 1 by 2r, as it is the length 110 from here to here, which again 1 atom by length is root 2a. That means 2 root 2r. Here from here to here 1 by 2 root 3 r. Note from above problem we can conclude that the crystalline materials are anisotropic because linear density itself is changing. Anisotropic in nature because difference in number of atoms per unit length in in different crystallographic directions. Family of directions, in a family all directions are having same material properties. 1 0 0 1 if family is represented by 1 0 0, then it can be said by 1 0 0 or 0 1 0, all combinations like this 0 0 1 1 bar 0 0 0 1 bar 0 0 0 1 bar, n is equal to 6. So if 1 represented by family of lines 1 1 0, then n is equal to 12. All combinations can be used, and we can include 1 bar once, 1 bar twice. We can do all combinations 1 1 1, then 8 combinations can be possible. Family of lines n is equal to 8. 1 1 1 1 1 1 bar, like that we can go 8 combinations. Question: an FCC copper material atomic radius r is equal to 0.1287 nanometer. Number of atoms per unit length in a direction of 101 is 101 is a face diagonal. So linear density, it passes through half half and 1 2. Number of atoms 2 by length is root 2a. A is equal A is equal to root 2a, which is also 4r. So 4 into 0.1287 is equal to 3.885 into 10 power 9 atoms per meter. Crystallographic plane Miller indices. It is a plane allocated with unit cell. Crystallographic planes are represented in terms of Miller indices. The Miller indices are complete integers obtained by reciprocals of plane fractions. Representation of single plane, normal bracket x y z. Representation of family of planes as flower bracket x y z. Here, as these are planes, no straight lines are used. To remember, just to remember, that is the technique. Miller indices procedure: locate origin O and x, y, z axis. Find plane fractions, plane dimensions p, q, r. Reciprocals of plane fractions 1 by p, 1 by q, 1 by r. Convert reciprocals into complete integers HKL. HKL are Miller indices. If we want to find this plane, then first find plane fractions. A by 3, 3a by 4, a. Reciprocals 3 by a, 4 by 3a, 1 by a. Multiply with 3a. 9 Miller indices 9, 4, 3. If 4 to 1 draw plane is given, then 1 2 by 4 1 by 4. So then inverse 1 to 4 1 to 4 1 by 4 1 by 2 1. Just do the reverse. 1, if 1 by 4 this is given, then we'll find in we will find reciprocals 4 to we will find reciprocals 4 to 1 reciprocate, and then we will find normal integers. First to find plane fractions, then reciprocals, then Miller indices. If Miller indices are given, then find reciprocals 1 2 by 4 1 by 4. Then plane fractions. Inverse 1 by 4 1 by 2 1. If plane inverse 1 infinity 1. Given plane is parallel to y. This means given plane is parallel to y axis. It is like this. Infinity 3a by 4 3 by 4 half 0 4 by 3 2. Miller indices here 0 4 6. 1 0 0. Plane fractions 1 infinity infinity. Given plane is parallel to y and z axis. Point infinity infinity minus a by 2 0 0 minus 2 inverse Miller indices 0 0 2 bar. Planar density is equal to number of atoms in a plane by area of plane. If it is 90 degrees like this, then 1 by 4 90 by 360. If it is covers half 180 by 360 half if it covers full 1. If it covers like this, then 0. Copper atomic radius of copper 0.1287. The density of material is 100 in 100. Plane of copper material is FCC 4R is equal to root 2a. Planar density PD is equal to 1 by 4 into 4 plus 1 by a square is equal to here 1 by 4 into 4 plus 1 by a square. Area of plane is equal to 2 by a square is equal to 2 by 8 r square is equal to 115.09 atoms per nanometer square. Determine planar density in BCC in a plane of 1 1 1. The atomic radius of BCC is r. Here only 60 we have to assume in 3D, only then we will get clear picture. 60 degrees, only 60 degrees will be covering this plane, so 60 by 360 is equal to 1 by 6. Planar density is equal to 3 into 1 by 6 by this area is equilateral triangle with each side root 2a is by root 3 by 4 into root 2a whole square is equal to root 3 by 16 r square. Body center atoms doesn't lie near plane. Imagine in 3D. Determine number of atoms per unit planar area and crystallographic plane of 1 1 1 in a face-centered cubic structure metal with atomic radius 0.125 nanometers. Its face-centered cubic 60 by 360 is equal to 1 by 6. 3 into half per unit planar area in crystallographic plane in a face-centered one. So here 1/6 contribution, but these three lines will cover half of them. This plane 3 into half plus 3 into 1/6 is equal to 3/2 plus 1/2 is equal to 2. This plane imagine in 3D. Interplanar spacing D, it is perpendicular distance between two parallel atomic planes. Cubic A is equal to B is equal to C. D cubic is equal to A by root of H square plus K square plus L square. DHKL planar parallel atomic planes. Tetragonal A equal to B not equal to C. D is equal to A by root of H square plus K square plus L square into A by C whole square. General equation DHKL is equal to 1 by root of H by A whole square plus K by B whole square plus L by C whole square. HKL Miller indices ABC lattice parameters. D110 is to D102 is to D111 A by root of 1 square plus 1 square is to A by root of 1 square plus 2 square is to A by root of 1 square plus 1 square plus 1 square. 1 by root is to 1 by 5 root 5 is to 1 by root 3. In FCC atomic radius is 1.2 angstroms. The planar spacing in a plane of 101 is D101 is equal to question mark is equal to A by root of 1 square plus 1 square is equal to 3 in FCC 4R is equal to root 2A, A is equal to 2 root 2 into 1.2 angstrom. 1 angstrom is equal to 10 power minus 10 meters is equal to 3.394 by root 2 is equal to 2.4 angstrom. X-ray diffraction method, Bragg's law. It is used to find type of crystalline structure in a material and chemical composition by determining interplanar spacing or lattice parameter of material. High energy, low wavelength X-rays are used in X-ray diffraction. N lambda is equal to 2D sin theta. X-ray source ray 1 or ray 2 HKL. E inversely proportional to lambda. N is equal to 1, 2, 3 order of reflection. Lambda is equal to wavelength of X-rays. D is equal to interplanar spacing is equal to A by root of H square plus K square plus L square. Theta is equal to Bragg's angle. 2 theta is equal to diffraction angle. A cubic structure material is examined under X-ray diffraction method with wavelength of X-rays used is 4 angstroms. The diffraction angle in first order reflection with the crystallographic plane of 111 is 60 degrees. Then calculate interplanar spacing and lattice parameter of material. 2 theta is equal to diffraction angle is equal to 60 degrees. Theta is equal to the Bragg's angle is equal to 30 degrees. And lambda is equal to 2d sin theta. Lambda is given 4 angstroms. So d is equal to 4 angstroms, which is equal to a by root 3. D is equal to A by root of H square plus K square plus L square for cubic. So A is equal to 4 root 3 is equal to 6.93 angstroms. In terms of planar spacing, D is given. Lattice parameter A is also we got A also. Crystallographic imperfections defects. First point defect, zero dimensional defect, 0D defect. Intrinsic defect, vacancy defect, Frankel defect, Schottky defect. Extrinsic defect, substitutional defect, interstitial defect. Line defect, 1D defect, dislocation, edge dislocation, screw dislocation. Surface defects, 2D defects, grain boundary defect, tilt boundary defect, twin boundary defect, stacking fault. Volume defect, 3D defect. Example, void. Point defects are generated by missing or misplacing of an atom from lattice structure. Intrinsic defects are generated inside material due to some external factors like increasing temperature. Vacancy defects NV temperature, as temperature increases, number of vacancy defects increases. Vacancy defects are generated by missing of an atom from lattice structure. The number of vacancy defects are increased in an exponential way with increasing temperature. The strength of vacancy defect material is decreased because of decrease in number of bonds. Because as atom is missing, then number of bonds are also decreased. Frankel effect are generated by misplacing a atom from its original position to interstitial position. The Frankel defects are mostly observed in ionic crystals. The strength of Frankel defect material may not be changed, but other properties are changed. F-central defect, color defect. This is generated by misplacing of an anion from its anion means negative from its original position to interstitial position by leaving one electron. Ionic crystal NaCl Na plus Cl minus. So leaving one electron, F central defect, it will go here interstitial position. Schottky defect. These are generated by missing pair of atoms, cation and anion, from lattice structure. These Schottky defects are generated only in ionic crystals. The strength of Schottky defect is decreased. The Schottky defect maintains electrical neutrality. Electrical neutrality. Plus or minus both are missing. So Schottky defect maintains neutrality. Extrinsic defect. The extrinsic defect are generated by adding foreign atom or impurity to the host material. Substitutional defect. These are formed by adding foreign atom or impurity atom in place of a host material atom replacement. The main condition required to form this defect is size of foreign atom is approximately same as host material atom. The strength of this defect may not change, but other properties are changed. Example, addition of chromium to iron forms substitutional defect. R foreign atom is almost equal to R host atom. Here HA R minus RFA less than or equal to 14%. Interstitial defect. These are generated by adding foreign atom or impurity atom at interstitial position by for host material. The main condition required to form this defect is size of foreign atom is much smaller than host material atom. The strength of this defect is increased, and not only strength but also other material properties are changed. Example, addition of carbon to iron forms an interstitial defect. Addition of carbon will be in interstitial position. Line defect, dislocation. Line defects are generated by missing line of atoms from lattice structure or accumulation of more than one point defect in a line. Dislocation, it is distributed region between two perfect crystals. Distributed region between two perfect crystals. Disturbed region between two perfect crystals. Burger vector, it is used to find direction and magnitude of dislocation. Here this is dislocation. This is dislocation line, this is dislocation atoms. Force is applied in this direction. In this direction, screw dislocation. In this direction, edge dislocation. BVST, BVED, Burger's vector. Edge dislocation, screw dislocation. In edge dislocation, the dislocated atoms are moving parallel to applied force. In screw dislocated atoms are moving perpendicular to applied force. The dislocated atoms are moving only in translatory manner. Edge dislocation, screw dislocation, the dislocated atoms are moving in translatory and rotatory manner in this direction, in translatory and rotational manner simultaneously. The Burgers vector line parallel to Applied force or perpendicular to dislocation line. This is dislocation line. This is Burger vector of ED. The Burger vector is perpendicular to applied force and parallel to dislocation line. This is BVST. The dislocation moment requires less force. As in this direction it's easy. The dislocation moment requires more force. BVST. Note the deformation material depends on dislocation up to elastic limit. The dislocation moment is present within the crystal, and by removing load, the dislocation reached its original position. Hence, up to elastic limit, the material regains back to its original position on removing load. Above elastic materials, above elastic limit, the material deform plastically because the dislocation reached out of the crystal. If within in the elastic limit within the crystal, by removing load, it will come back. Less than elastic, it will move back to position. If greater than elastic limit, it will move out. Slip system. The slip is a dislocation movement in a easy manner that requires low energy. The dislocation always move in a direction and on a plane that requires low energy. The combination of slip directions and slip plane is known as a slip system. The slip system is closely packed direction and slip plane is a closely packed plane. Example, the slip system of FCC is 110, 110 and 111. This is line. This is plane. 110 between 100, 110, 111. 110 is closely packed. So this is closely packed direction, slip direction 110. Planes 100, 110, 111. This is closely packed. So 111 is closely packed. This has 8 combinations. 8 combinations. In these 3, 110, this slip plane each has 3, 12 systems. Structure, number of slip systems: HCP 3 brittle, BCC 48, FCC 12. These two are ductile. BCC 48. If number of slip system is more than 5, those materials are ductile in nature, otherwise the material are brittle. Even though FCC materials have lower number of slip systems than BCC material, FCC are more ductile because FCC is closely packed structure with more number of active slip systems. So FCC is more ductile. Grain and types of grain material. Grain. In a grain, atoms are arranged in regular periodic manner, but orientation of atomic planes of one grain is different from adjacent grain. Grain boundary. It is disturbed region between two perfect grains of different atomic orientation. The bond length between two atoms at grain boundary is more than inside grain, and hence boundary atoms have low bond strength, and to break these bonds require low energy or force, and hence grain boundaries are weak regions in a material. Due to more bond length, boundary atoms have high energy, and external oxygen atoms easily react with boundary atoms, forms oxide or corrosion. Grain boundary, here it may form like this. Fine grain fine grain materials fast cooling, coarse grain materials slow cooling, are formed from by slow cooling. Here crack, these grain lines only crack can form. Fine grain material, coarse grain material. Fine grain materials have smaller grain size with more grain boundaries. Coarse grain material, these will have larger grain size with less grain boundaries. The fine grain materials are produced by fast cooling of material. The coarse grain materials are produced by slow cooling of material. At room temperature, fine grain materials have a high strength because more grain boundaries, and at each grain boundary dislocation moment is obstructed. At room temperature, coarse grain materials have low strength because less grain boundaries, and due to that dislocation movement is easy. At high temperature, fine grain materials have low strength because more grain boundaries. At high temperature, more boundary atoms break bonds due to that slip deformation and grains takes place. At high temperature, coarse grain material have high strength because of less grain boundaries due to that low slip deformation. Hall-Petch equation. It gives the relation between strength of materials with grain size at room temperature. Sigma is equal to sigma naught plus k by root d. Sigma is equal to strength of material, sigma naught comma k constant for material, d is equal to grain size. The strength of material at grain size of 36 microns is 250 megapascal. Same material grain size is increased to 64 micrometer, then strength is decreased to 150 megapascal. What is strength of material at grain size of 49 micrometer? Sigma 1 is equal to sigma naught plus k by root d. Everything is given, just substitute values. ASTM grain size number. As per American Standards of Testing Material Organization, number of grains per unit area in a material is measured from ASTM grain size number. N is equal to 2 power n minus 1 at a magnification of 100 times. Capital N is equal to number of grains per inch square. Small n is equal to ASTM grain size number. M is equal to 1. M is equal to 100x, A is equal to 1 inch square, A is equal to 1 inch square. M is equal to 500 times A is equal to 1 inch square. N inversely proportional to M square. Nm into M by 100 whole square is equal to 2 power n minus 1. M is equal to magnification. Determine number of grains per inch square if ASTM grain size number is 8 with no magnification. N1 into 1 by 100 whole square is equal to 2 power 8 minus 1. N1 is equal to 12 12,800,000 grain per inch square with a magnification of 100, and 100 is equal to 2 power n minus 1 is equal to 2 power 7 is equal to 128 grains per inch square. Determine ASTM grain size number if number of grain per inch square is 20 at magnification of 400. 20 into 400 by 100 whole square is equal to 2 power n minus 1, n is equal to 9.32. Surface defect. Surface defects are generated by missing of multiple atoms in a plane or accumulation of more than one line defect in a plane. Tilt boundary defect theta less than 10 degrees. In tilt boundary defect, the grain orientation mismatch angle is small, theta less than 10 degrees. The tilt boundary defects are formed due to accumulation of edge dislocation. There is no mirror image of atomic plane on both sides of defect. Twin boundary defect theta greater than 10 degrees of like this, it will be like this. In twin boundary defect, the grain orientation mismatch angle between two grains is large. Twin boundary defects are formed due to accumulation of screw dislocations. There is mirror image of atomic planes on both sides of defect. Stacking fault FCC 110. In a stacking fault defect material, the atomic planes are displaced with some distance without change in parallelism. Mismatch angle is 0 degrees. We miss. Okay. Volume defects are generally generated by missing of plane of atoms in all three directions, or accumulation of more than one plane of atoms. Example: void. Material properties and testing. Theoretical density. The theoretical density of a material is calculated by considering unit cell of material. Mass by volume of unit cell is equal to N into AW by VUC is equal to N into AW by AN by VCC is equal to N into small n into AW by AN into VUC. AN is equal to Avogadro number. 1 mole is equal to 6.023 into 10 power 23 atoms. AW is equal to atomic weight. N is equal to effective number of atoms. VUC is equal to volume of unit cell. FCC material metal atomic weight is equal to A, atomic radius is R, then the theoretical density of material is N is equal to Avogadro number. Low theoretical is equal to small n into AW by AN into VUC is equal to A by N into 4 by A cube. A root 2 is equal root 2A is equal to 4R. A is equal to 2 root 2R. A by N into 1 by root 2 into 2 into 8 into root 2 into 2 into R cube. A by 4 root 2 NR cube. A metal having diamond cubic structure has a metal having a cubic structure has a density of 1.892 and atomic weight of 132.91 gram per mole. Lattice parameter is 6.13 angstroms. Determine crystal structure of metal. 1.892 is equal to n into 132.91 by Avogadro number 6.023 into 10 power 23 into A cube 6.13 cube angstrom 10 power angstrom 10 power minus 8 meter. So 10 power minus 24. 1 angstrom is equal to 10 power minus 8 centimeters. 10 power minus 8 centimeters is equal to 10 power minus 10 meters. 10 power minus small n is equal to 2. So BCC cubic structure now. Young's modulus based on elasticity. Engineering materials are two types: linear elastic material, non-linear elastic material. The linear elastic material are following Hooke's law, that is stress directly proportional to strain up to proportionality limit. The stress strain curve is linear straight line up to proportionality limit. The Young's modulus of these material are calculated by considering slope of stress strain diagram curve up to proportionality limit. Example: all types of steels. Non-linear elastic material. The non-linear elastic material are not following Hooke's law. The stress strain curve is a curved line. The Young's modulus of these materials are calculated by considering slope of tangent and or secant lines to the stress strain curve. Example: polymers, cast iron, ceramics, and concrete. Proportional element, elastic limit E is equal to d sigma by d epsilon. Tangent method, tangent is drawn, that slope is considered. Secant method, secant is drawn, and that method. Sigma, epsilon, low carbon steel or mild steel, it will be like this. High mild carbon steel, it will be like this. High carbon steel, it will be like this. E is same, so it will be like this. True stress, true stress and strain diagram. A is equal to pi by 4 d square lg is equal to 5.4 root Ag dg. Sigma t is equal to f by pi by 4 df square. Sigma e is equal to f by pi by 4 dg square. This is true stress, this is engineering stress. F Vi is equal to AILI, Vf is equal to AFLF. True stress is equal to load applied by instantaneous area. Engineering stress is equal to load applied by initial area. Sigma epsilon, this is sigma e epsilon e diagram, sigma t epsilon t diagram. It will be like this, then it will keep on increasing go up upper limit, then also keeps on increasing. True stress sigma t is equal to f by af into ai by ai is equal to f by ai into ai by af. Sigma t is equal to sigma e into ai by af. In GATE 2019, one question asks sigma t is equal to sigma e into di square by df square. AI li is equal to af lf. AI by af is equal to li by lf. Sigma t is equal to sigma e into lf by li. Delta L is equal to LF minus Li. LF is equal to delta L plus Li. Sigma T is equal to sigma E into delta L plus Li by Li. Sigma T is equal to sigma E into 1 plus delta L by Li. Sigma T is equal to sigma E into 1 plus epsilon E. Here epsilon E is longitudinal strain is equal to delta L by Li. True strain, it is instantaneous strain from Li to Lf. Epsilon t is equal to integral Li to Lf dl by L is equal to ln L Lf to Li. Epsilon t is equal to ln of Lf by Li is equal to ln of Li plus delta L by Li. Epsilon t is equal to ln of 1 plus dl by Li. Epsilon t is equal to ln of 1 plus epsilon e. A metallic rod of diameter dy subjected to tensile test. The engineering stress and true stress at fracture are 800 megapascal and 900 megapascal respectively. The ratio of rod diameter at fracture df to initial diameter is sigma t is equal to sigma e into dO by df whole square. Df square by dO square is equal to 800 by 900. Df by dy is equal to 0.943. A metallic rod of 10 diameter is subjected to a tensile test at an engineering stress of 400 megapascal. The diameter of specimen is 8 Determine true stress and true strain of masses. Sigma t is equal to sigma e into dO square by df square. Is equal to 625 megapascal. Epsilon t is equal to ln of 1 plus epsilon e is equal to ln of lf by li is equal to 2 ln dO by df. 2 ln dO by df is equal to 0.446. Power law of strain hardening. Input output rolling. Elastic limit to upper yield, elastic from elastic limit to ultimate point. Proportionality sigma t epsilon t Hooke's law up to elastic limit. It will go like this. Then ultimate point neck, from here necking. Elastic limit to ultimate point strain hardening up ultimate point to fracture point necking. Epsilon, this is necking. Epsilon t necking is equal to n. Sigma d directly proportional to epsilon t power n. Sigma t is equal to k epsilon t power n. Only true sigma epsilon. K is equal to k is equal to constant for a material. N is equal to strain hardening exponent 0 less than or equal to n less than or equal to 1. HCP n is equal to 0.05. BCC n is around 0.25. FCC n is around 0.5. Net necking epsilon t is equal to n. Sigma t is equal to k epsilon t whole power epsilon t. Sigma t is equal to k n power n. The power law of strain hardening gives relation between true stress and true strain of material in plastic region. It is applicable prior to necking point. The strain hardening exponent is also known as work hardening exponent. It is constant material property. It is a true strain at a necking point for ideal stress strain curve. Strain hardening mechanism. It is one of strengthening mechanism. In this process, the material is deformed plastically by applying loads. Dislocation density is increased due to application of for up mechanic applied due to applied mechanical forces and due to large number of dislocations in a material. Dislocation interaction takes place, and due to that repulsive forces are generated between dislocation, and dislocation movement is arrested. Hence, with increasing load, a material strength and hardness is increased in plastic region up to necking point. Large number of dislocations are accumulated at grain boundary and form dislocation forest, and due to that also dislocation movement is arrested at grain boundary, so that strength and hardness of material are increased, but large internal stresses or residual stresses are generated. The strain hardenability of material is directly proportional to strain hardening exponent. So strain hardening directly proportional to n. CW cold workability of FCC greater than cold workability of VCC greater than cold workability of HCP. Ductile dislocation forest. The strength of material is increased in following ways. Strengthening mechanisms. Alloyings. The strength of material is increased by adding alloying elements to the host material. 1841 high speed steel, percentage wolfram, percentage chromium, percentage vanadium. Tungsten high temperature strength. 18% tungsten, 4% chromium, 1% vanadium. Grain refinement. The strength of material is increased by changing grain structure by applying heat treatment. Strain harden. Third, strain hardening. So for strengthening, alloying grain refinement, strain hardening. True stress and strain relation is given below. Sigma t is equal to 10 T for epsilon whole power 0.8. The initial area of specimen is 100 mm square. Then the area of specimen at necking point is epsilon is equal to 0. Epsilon true is equal to 0.28 is equal to ln LF by LI is equal to ln AA by AF. From that we can get AF. For some metal alloy, a true stress of 415 megapascal produces a plastic strain of 0.475. How much will a specimen of this material will elongate? Will elongate when a true stress of 30 will elongate means delta L, not LF. N is equal to 0.25. Original length 300 nanometers. K is equal to sigma by epsilon whole power n. We will get K. Epsilon true is equal to 325 by 499.89 whole power 1 by 0.25. When true stress is 325, then 0.178. For a brass alloy, the following engineering stress produce corresponding plastic engineering strains. Okay. engineering strains. Okay, on basis of this information, stress necessary to produce engineering strain of 0.25. Plastic is should be underlined. So sigma T1, sigma T2 find out, epsilon T1, epsilon T2 find out, then find N, then find K. Epsilon E is equal to 0.25, then epsilon T is equal, we'll get epsilon T. From that sigma T, from that sigma E. Toughness per sigma epsilon toughness per volume is equal to modulus of toughness units Newton per meter square sigma into epsilon Newton per meter cube. It is the ability of material that can absorb energy or impact energy up to failure point. It is it is calculated by considering area of stress strain curve up to failure point. The area of stress strain curve represents toughness per unit volume. It is known as modulus of toughness. The toughness is an extrinsic property of material, that is toughness of material also depends on dimensions or volume, but modulus of toughness is intrinsic property of material. Modulus of toughness is intrinsic property of material. That means it does not depend on volume dimensions. Sigma epsilon p delta area can be calculated from this triangle and this square. Measurement of toughness of brittle material. The area of stress strain curve of a brittle material is very small and it is not possible to measure the area, and hence area method is not suitable to measure toughness of brittle material. The toughness of brittle material are measured by impact testing. Sigma epsilon cast iron, it will be like this. Impact test, ISO test, E2 is equal to WH2, E1 is equal to WH1. It is released from here and it goes till here. Toughness is equal to W into H1 minus H2 because this energy is lost. Charpy test simply supported by it will be like this notch. In ISO test, specimen is positioned like a cantilever beam. And at the middle of specimen a notch is created to initiate crack and to reduce the weight of hammer. ISO test is not more accurate because of non-uniform distribution of loads in the specimen. In Charpy test, the specimen is positioned like a simply supported beam and at the middle of specimen a notch is created. The Charpy test is more accurate method because of uniform distribution of loads. The toughness of a ductile material is measured by area method, and toughness of a brittle material is measured by impact test method. Resilience, it is ability of material that can absorb energy up to elastic limit. It is calculated by considering area of stress strain curve up to elastic limit. A sigma epsilon elastic limit. Proof resilience, it is ability of material that can absorb energy up to proportionality limit. Proof resilience, it is calculated by considering area of stress strain curve up to proportionality limit. Sigma epsilon up to proportionality limit. Ductility, it is ability of material that can deform plastically up to failure point by application of tensile loads. F less than or equal to elastic limit. F less than or equal to elastic limit di li. F greater than elastic limit DLF and DFLF. From elastic limit till here, plastic deformation, ductility. Measurement of ductility, percentage increase in length, percentage elongation. LF minus Li by Li into 100 is equal to epsilon into 100. percentage decrease in cross-sectional area AA minus AF into 100 into 100 by AA is equal to 1 minus AF by AA into 100 is equal to 1 minus DF DF by DA whole square into 100. Malleability, it is ability of material that can deform plastically in lateral direction up to failure point by applying compressive load. Malleability Variability is measured by considering percentage decrease in length and percentage increase in cross-sectional area. If you will compressive length, compressive load, then malleability. Hardness, it is ability of material that can resist scratch or indentation or penetration on surface of material. Hardness is a surface phenomena, and that is only surface atoms are participating in the mechanism. Note, strength, it is ability of material that can resist failure. The strength is volumetric phenomena, that is complete volume of atoms are participating in mechanism. Complete, okay. Stiffness, it is ability of material that can resist deformation. The stiffness is extrinsic property of material because that depends on dimensions. The stiffness of material is directly proportional to Young's modulus. Ability to resist deformation. Stiffness. Strength, ability that can resist failure. Measurement of hardness, P Mandel indenter tool, workpiece area of penetration, AP. Hardness, P is equal to P by AP, unit kg per meter cube, kg per mm cube, mm square, or Newton per meter square. Kg per mm square or Newton per meter square. Strength directly proportional to hardness. Steel UTS is equal to 3.5 BHN. 3.5 UTS ultimate is equal to 3.5 BHN. Hardness test, indentation tool, tool shape, applicable material, principle, formula, diagram. Brenel test, low hard and medium hard materials. Hard indentation tool, hardened steel. Spherical capital is equal to 10 mm. 10 mm. Applicable material aluminum, copper, brass, mild steel. Principle based on penetration area. BHN is equal to 2p by pi capital D into capital D minus root of capital D square minus small d square. Small d is equal to indentation diameter. AP is equal to pi by 2 into capital D into capital D minus root of capital D square minus small d square. Vickers test, high hard material, diamond, tool shape pyramid 136 degrees, 136 degrees, SIC, WC, TIC, CBN, SI3 and 4 based on indentation diagonals. VHN is equal to 1.854 P by D average square. D average is equal to D1 plus D2 by 2. Rockwell test, all types of material, diamond, conical, 120 degrees, medium carbon steel, high carbon steel, alloy steel based on depth of penetration. RHN inversely proportional to dp, depth of penetration workpiece P. A Brenel hardness 10 mm, every okay, small d, capital A, W, everything is given. Weight load is 500 into 9.8. From that we can get kg per mm. If we can represent in kg per mm square also. MHO test, more test, scratch test. It is preliminary qualitative test. Use it to analyze used to analyze the type of hard material by applying scratch on the surface of material. This method is also used to find hardness of very high brittle materials. Show test, soft polymer, example rubber PVC. Barcode test, hard polymer, example bakelite. Noob test, micro materials. Noob test micromaterials. Creep 10 kg constant load delta is equal to WL by 48 EA. It is deformation with respect to time at constant load. Either at constant room temperature or high temperature, the creep is slow and progressive deformation. Strain lifespan time 1 CR 1 2 3 CR decreases 1 CR constant CR increases room temperature. High temperature it will increase like this. In first region of creep curve, the creep rate is decrease in mode because of strain hardening. In second region of creep curve, the creep rate constant, is in steady mode or constant mode. In third region of the curve, the creep rate is increasing mode or transient mode because of neck formation. The creep is bad phenomena for a material, and creep resistance is increased by using high strength and high Young's modulus material. Using fine grain material for room temperature creep resistance, using coarse grain material for a fine grain for room temperature, using coarse grain structure material for high temperature creep resistance, adding refractory metals to host material for high temperature creep resistance. The refractory metals are very high melting point temperature metals used for high temperature application purpose. Refractory metals are 4 out of 118 elements: tungsten 3500 degrees centigrade, niobium, tantalum, molybdenum. Niobium, tantalum, molybdenum. Proof stress. Proof stress is the yield strength of a medium carbon steel and a high carbon steel. It is measured by using an offset method or a parallel line of at a parallel line to stress strain curve is drawn from an offset point 0.2% as strain, that is epsilon is equal to 0.002 on x-axis. The parallel line intersects the stress strain curve. The stress corresponding to intersecting point represent proof stress or yield strength of material. At 0.2%, 0.002, draw a straight line parallel to E. It will intersect mild carbon steel and high carbon steel at sigma y, which is equal to proof. For design of material, lower yield point of mild steel is considered as yield strength because lower yield point is a static point, upper yield point is not a static point. In mild steel, most of the carbon atoms occupy at dislocation region. This due to that more force or load is required for dislocation movement. Due to that, the stress of material is increased up to upper yield point. At upper yield point, dislocation moved from initial state to the low carbon region, so that less force is required for movement of dislocation, and hence stress strain curve is downward slope from upper yield point to lower yield point. Here to here. Force carbon atoms, it will move till here.